Dear colleagues, your attention is invited to the work Predicate clustering method and its application in the system of artificial intelligence by Proniuk, Nataliia, Iryna, Kyrychenko, Glib, Tereshchenko. In recent years, great attention has been paid to the development of new methods for parallel information processing. Practically all existing approaches are based on the concepts of decomposition and composition in one way or another, be it programming, databases, neural networks, and so on. Therefore, the development of new theoretical methods of decomposition is a highly promising and interesting direction in algebraic logic. This work proposes a new method of multilayer decomposition of predicates, which will be obtained from the generalized properties of comparator identification. Allow me to present this methodology sequentially. In predicate algebra, comparator identification is widely used, which is a type of indirect identification. A comparator key is a device with m inputs and one output t, where t is the binary reaction of the comparator. The comparator determines whether its input signals are in a given relation key or not. Comparator identification is successfully applied in solving many artificial intelligence problems. This method is designed for investigating objects with input signals that are inaccessible for direct measurement. The subject of such identification is often the human intelligence. In predicate algebra, during the comparator identification process, the identifiable object P implements a predicate, referred to as the predicate of object P. Let us consider the main concepts that will help us generalize the method of comparator identification to a wider class of predicates. It is known that any predicate, as mentioned in the formula 2, is an equivalence predicate. The function f is called the characteristic function of the equivalence predicate. In predicate algebra, any equivalence predicates and only they can be represented in the general form. Above, it has been shown that a pair where a characteristic function determines a unique equivalence predicate. However, does every equivalence predicate E uniquely determine the pair? It turns out no. There exist different pairs that define the same equivalence predicate E. The property formulated below specifies the necessary and sufficient condition under which two pairs determine the same equivalence predicate E. Statement 1. You can see it on the slide. From statement 1, it follows that if the equivalence predicate E can be represented as formula 2, then it can also be represented as formula 3. To solve problems of comparator identification, an important question is the issue of isomorphism of equivalence characteristic functions. Statement 2. You can see it on the slide. In essence, this property means the following. Two different descriptions of the same identifiable system P, whose input signals are defined on non-intersecting domains, always coincide up to strong isomorphism. That is, they coincide up to the designation of input signals x and y of the system P, described in a unified notation system. The substance of this and other statements in work means that the behavior of predicate on the formula 2 of the identified system is fully determined by the action of the identified object f, and vice versa. Thus, a comparator identification method is described for mathematically describing subjective phenomena. Human behavior in many cases allows description using an equivalence predicate. The question arises, is there another general form of a binary predicate, and what is it? Undoubtedly, there must be some general expression that gives some binary predicate. To answer this question, consider the following concepts. Let us consider an arbitrary binary predicate P defined on Cartesian products of two sets and seek a representation for it, in which the comparison of the values of the two corresponding functions f1 and f2 is carried out using a simple predicate in some sense. This predicate should replace the equality predicate in formula 2. In order to obtain the required form of the predicate, let us consider several important concepts. Statement 3. You can see it on the slide. Theorem 1. You can see it on the current slide. Expression 5 represents the general form of a binary predicate P. Surjections f1 and f2 are called the characteristic functions of predicate P. Theorem 1 can be extended to the case of an arbitrary n-ary predicate. In this case, the theorem can be formulated as follows. The following property mentioned in the statement 4 states that by this comparator identification method, n objects can be identified exhaustively. That means up to notations. Identification of human intellectual activity using this scheme opens the way to a mathematical description and artificial reproduction of such important aspect of the mind for machine intelligence as perception, understanding, recognition, and awareness. A two-layer decomposition of a first-order predicate is called its decomposition into characteristic functions and images, according to its general first-order form. Second-order predicate two-layer decomposition. The question arises, what form will the predicate take if an arbitrary mapping is used instead of surjection? To answer this question, the general form of the predicate needs to be slightly modified. The following statement provides the required modified form of the predicate. Statement 5. You can see it on the slide. And vice versa. The predicate f is called the characteristic predicate of the equivalence. It uniquely determines the characteristic function f of the equivalence. It is important to have a method for constructing the characteristic predicate for any equivalence. In conclusion, it should be noted that the general form for the most general case of a symmetric predicate, that means the quasi-tolerant predicate, has been obtained. If we remove the last restriction, the symmetry of the predicate E, the following theorem will be valid. Theorem 2. You can see it noted on the current slide. The formula 7, which represents the general form of a second-order predicate E, can be expressed differently as formula 8, where dB is defined in the formula 9. This theorem is very useful describing the structures of many information objects, such as databases, microchip design, etc. In the previous sections, two types of two-layer decomposition of predicates were considered, the first and second types. Their combination results in a three-layer decomposition of the predicate. The first type of decomposition into formula 5, where f1 and f2 are functions, and L is a simpler predicate than E. The second type of decomposition transforms the predicate E into a construction of the form in the formula 8. Thus, a three-layer decomposition gives a representation of the predicate E as formula 10. We will interpret the obtained result in technical terms. The signal transformer E, mentioned in the figure 1a, is transformed into a two-layer connection of blocks with intermediate signals, figure 1b. The signal transformer L, in turn, is transformed into a two-layer connection of blocks. As a result, we obtain a three-layer connection of blocks with intermediate signals, on the figure 1c. In it, the blocks are included in reverse order. Above, it was shown how the functions J1 and G2 are practically sought. Thus, a method was developed for constructing schemes that implement arbitrary relations, and relations, as is known, represent a universal tool for modeling any object and any processes. The mathematical results of the work can be used in systems for automatic processing of textual information. It is well known that predicate logic is a natural and convenient tool for modeling natural language relations. Our task is to formally describe the morphological predicate P, which is the model of fractional processing of Ukrainian adjectives. Thus, it is necessary to form a three-letter ending Z of the word form X, depending on the set of grammatical features Y. In the Ukrainian language, there are 24 endings of complete non-possessive adjectives. The influence of the word X of the first, second, and third letters of the ending can be unambiguously characterized by the set of features X, where X1 is the feature of the last letter of the stem with values of letters on the screen. You can see it on the slide. X2 is the feature of the stress on the stem with values of Y stressed, B unstressed. X3 is the feature of softening of the stem with values of M soft, M hard. Let's write the domains of the introduced variables as formula 11. Linguistic studies have shown that it is necessary to introduce four grammatical features Y that unambiguously characterize the influence of the distant text Y on the ending Z, where Y1 is the case, Y2 is gender, Y3 is number, Y4 is animacy. Let us write the domains of definition for the introduced variables as formula 12. The morphological predicate P corresponds to the function Z. In order to express this function in a compact form, we will use the first-order two-layer decomposition. Let us introduce the functions a of x and t of y. Now let us write net function, but first, to avoid cluttering the notation, we introduce some symbols in the formula 13. It also should be noted that in the Ukrainian language there are no adjectives with stems that end in letters on the slide. You can see it. or a soft consonant in an unstressed syllable. Taking into account that aforementioned fact and the introduced notations, the function a will be expressed as formula 15. The function will have the form in the formula 15. Formulas 14 and 15 show that a word affects the endings of the full form of non-possessive adjectives in 6 different ways, and a text in 14 different ways. As a result, we get a function of the following form, in the formula 16. Thus, formulas from 11th to 16th form a model of the flexion of adjectives in the Ukrainian language. The result obtained in this work can find broad application in various areas of human activity related to computer and information technologies. The most promising direction is the creation of a new generation computer based on the principles of parallel information processing. Clearly, if various regularities of natural languages are described using the two-layer decomposition method of first and second order predicates, and microprocessors are built on this basis, they will be able to perform the functions of certain structures of human intelligence that participate in the implementation of corresponding aspects of human language activity. And conclusions. The scientific problem of developing algebraic methods for predicate decomposition for the formal analysis of information processes, particularly for the formal representation of natural language text semantics, has been solved in this work. A series of theorems have been considered and proven, characterizing the method of comparator identification, which is a method suitable for studying and modeling subjective states of a person. This general form of the predicate is a new model of comparator identification. The relationship between the types of isomorphism of the model of comparator identification and the practical features of measuring input signals has been investigated, which allow the theory of comparator identification to be developed for a wider class of objects. We were also able to present the predicate in its general form of the second order, which gives the researcher even more opportunities for formalizing any relations in logic algebra. The combination of the two-layer decomposition of the first and second kind made it possible to obtain a three-layer decomposition of any predicate of any dimensionality. The development of formal representation methods for arbitrary relations and their subsequent schematic implementation contributes to the development of artificial intelligence systems and the improvement of the process of automated design of digital devices, which can in particular be part of an intelligent interface, computer-aided design, and learning systems, expert systems, decision support systems, etc.